today we are continuing with module 5, which is the first module in the second part of this Wi-Fi technology fundamentals course. We are continuing to talk about the advanced MAC features that are part of the Wi-Fi standard. So, today's session we're going to talk about the Wi-Fi 6E, or the new 6 GHz spectrum, and the new features in the 6 GHz spectrum. So just before we go into the details of today's session, let's just quickly recap what we talked about in the last session. The last session was about Wi-Fi 6, or also referred to as 11AX. And in 11AX, we talked about primarily the features of OFDMA, multi-user MIMO, and so on. So the main goal of 11AX was not only to improve throughput, but also improve efficiency and better spectral efficiency, that is, and also allow for hundreds of users to connect to an access point. So a typical Wi-Fi 5 or Wi-Fi 4 access point was designed to serve, let's say, 20, 30, 50 Wi-Fi stations, practically speaking. The idea of Wi-Fi 6 was to be able to support hundreds of Wi-Fi clients on a single access point. And this was the time when we were starting to see IoT devices and low-end Wi-Fi devices coming onto the network. And the idea was not only are we going to get really high throughput, but we also should be able to support low-end devices that really don't need much throughput, but are very latency sensitive. And we should be able to support hundreds of devices on a single access point. That was the whole idea of Wi-Fi 6, and OFDMA was the technology that was trying to enable that, where in OFDMA we have this idea of multiple users being able to split the available channel bandwidth into smaller, what we refer to as groups of tones, or what we refer to as resource units. And this allows multiple users to use smaller chunks of frequencies and successfully transmit and receive from the access point at the same time. So if there are multiple users able to transmit at the same time and receive at the same time, then that would reduce the queuing time for the traffic that's buffered to the access point, and also reduce the overall latency and improve the user experience. So we talked about how OFDMA works. We explained the changes in OFDM between Wi-Fi 5 and Wi-Fi 6, the spacing between the subcarriers, and also the guard intervals, and a number of other changes have been made between OFDM in Wi-Fi 5 and Wi-Fi 6. And we also talked about how uplink OFDMA works and how downlink OFDMA works, how the concept of trigger frames, the concept of RU allocation, that the access point will do RU allocation using multi-user. Basically, it will send a multi-user RTS frame where it will allocate different number of RUs to different users, and the users have to send a CTS frame. And then once that exchange is done, you will have a simultaneous communication of information. So we talked about uplink OFDMA, downlink OFDMA in detail. And then we explained the concept of multi-user MIMO, how multi-user MIMO uses the spatial diversity to actually transmit, meaning if there are multiple devices, stations all around the access point, the AP can transmit simultaneously to multiple stations and beamform the signals in an orthogonal way so that it can actually transmit to multiple devices at the same time. So if this access point is, let's say, a 3x3 or a 4x4 MIMO access point, it should be able to successfully talk to 4 1x1 devices that are in various locations around the access point and beamform signals to them simultaneously, and then improve your throughput by using the spatial diversity. So we explained that in detail, and also explained how uplink and MIMO works in conjunction with OFDMA. And then 1024 QAM is the new modulation rate that improves the overall throughput, and talked about how 1024 QAM works. And the idea is that the higher the modulation rate, the better signal to noise ratio that you will need, and which means that you cannot go very far. So really 1024 QAM can be used when you're very close to the access point. And then we talked about this concept of BSS coloring. The idea was that when you have a large scale Wi-Fi deployment with lots of access points, and remember in 2.4 and 5 GHz bands, we have limited non-overlapping channels, especially if you're using 40 MHz, 80 MHz, and 160 MHz channels, you have limited non-overlapping channels. So the idea is that as you deploy lots of access points close to each other, there will be reuse of frequencies. And the idea of BSS coloring is any particular client device can decide to either back off or not back off from another access point that is in the same channel based on the color codes. So you can actually code, allow different color codes to each access point that is operating in the same channel. And when the client is trying to communicate with access point 1, if it sees another access point in the same channel, but also using the same color, then it will decide to back off. But if it's seeing another access point in the same channel, but using a different color, the idea is that it is safe to even transmit, and the signal energy detecting is still not that high to interrupt your communication. So using the concept of coloring, you're deciding if it is safe or not safe to transmit on overlapping channels. And that's the idea of BSS coloring. So we talked about how the color coding works and how that color codes are added to the information elements and so on. Then we also talked about TWT, which is a more advanced kind of power save mechanism. The idea here is a legacy power save. The stations have to wait for the beacon periods to see if the data is buffered, and they have to wake up based on the AP's schedule. The idea of target wake time was to basically for the station to decide and negotiate a particular pattern or a particular schedule with the access point, and that way the station can wake up as per the schedules. We talked about all of these features in fair bit of detail. So if anyone missed this session, you can go back and watch the video. The video should be uploaded on the website, and also the slides should be there. For those of you who are joining for the first time, of course, you can stay connected by accessing the course web page. If you're not registered, you can register using the links, and also join the WhatsApp group if you want to get more communication about the course. Right. So now getting into today's session, we are continuing on this slide where we are following this. What are the new things that are in Wi-Fi 4, 5, 6, and 7? So last session, as we talked about, was Wi-Fi 6. Today we're going to talk about Wi-Fi 6E, and then next week we're going to talk about Wi-Fi 7. So if we really look at Wi-Fi 6E, it's nothing but an extension of Wi-Fi 6 from fundamentally there's not a lot of changes, but the biggest most exciting thing that came out in Wi-Fi 6E was the opening up of the 6 GHz spectrum, and that opened up so many possibilities for Wi-Fi. So today, the entire session, we're going to talk about what happened and how did the 6 GHz spectrum open up, and how does that affect Wi-Fi, and basically what new features have been added to accommodate the new things that are coming out of the 6 GHz spectrum. So that's what we're going to talk about today. So going back into history, if you look at Wi-Fi unlicensed spectrum allocation, so around the 1980s, basically we had some part of the 2.4 GHz band and some part of the 5 GHz, the 5.8 GHz band open up for unlicensed use. Of course, the frequency spectrum is used by other technologies like Bluetooth and cordless phones, microwave ovens, and so on. But it was also available for using for Wi-Fi. And then about 10 to 12 years later, then we have some more spectrum open up in the 5 GHz band, and then later in 2003 there was more spectrum that opened up in the 5 GHz band. So if you add up all the spectrum that was available up until the early 2000s, between 2.4 and 5 GHz, that's only about let's say 600 megahertz of spectrum. Now Wi-Fi 6E came along, the 6 GHz spectrum came along in 2020, and this is why it is so exciting. And when the spectrum was released, there was so much discussion about this in the Wi-Fi community, and everyone was so excited. The main reason here is that we have like 1200 megahertz of clean spectrum that is now opened up in the 6 GHz band, which is much higher than anything that was available for Wi-Fi in the past. So as Wi-Fi enthusiasts, if we can imagine how much revenue and how much business that Wi-Fi has generated over the last 20 years, just based on the spectrum that was allocated so far, and now we can only imagine how much more opportunities and business cases that this new spectrum will open up, because there's now a lot more spectrum available in the 6 GHz band for unlicensed use. So if you take this 1200 megahertz wide frequencies, so let's go into a little bit more detail of where the spectrum is allocated. So it's allocated between the 5.9 and the 7.1 area. That gives you about 1200 megahertz. So 5.9 gigahertz and 7.1 gigahertz space. So that's about gives you about 1200 megahertz of spectrum here. If you see, put things in perspective, that is 59 20 megahertz channels. So in 2.4 gigahertz, we only had 3 non-overlapping channels in the 2.4 gigahertz. Now the 6 gigahertz spectrum, we have 59 channels, right? That's a lot of 20 megahertz channels that are available. And if you're using channel bonding, of course, we're doing 40 megahertz, then you have 29 channels. And then if you're using 80 megahertz, you have 14, and 160 gives you 7. And then the new Wi-Fi 7, of course, if you're doing 320 megahertz channels, then you'll get about 3 channels. So that is a lot of frequency channels that are available for unlicensed use in the 6 GHz. This is the reason why 6 GHz spectrum is so exciting. Now again, one more time, comparing it with the previous technologies, 2.45, 6 GHz is again opens up so much opportunities here. Again, comparing 20 megahertz, only 3 non-overlapping channels in 2.4, but 59 non-overlapping channels in the 6 GHz band. So that gives us a lot of spectrum to play with, and which means that if you want to think about it, if you are deploying 20 megahertz channel bandwidth access points, you can actually deploy 59 access points in the same location without each of them interfering with each other in theory, because they're all using different channels. So that is how dense you can do deployments. Of course, most APs don't use just 20 megahertz anymore, so they use 40 megahertz, 80 megahertz, but still you can still get a lot of non-overlapping channels with one area, and which allows you to do very dense deployments. Now 6 gigahertz adoption is picking up, and over the last 3 years, and this slide I found on the internet, I think is data from July 2023, so it's a bit last year. So as of that date, about 70 countries have already adopted, are in the process of adopting 6 gigahertz. It's in India, it's not quite there yet, but hopefully sometime this year it may possibly happen. But it is slowly picking up, and not every country opened up all the bands on the 6 gigahertz, and every country has different rules. But in general, the adoption is really picking up, and more and more countries are starting to basically open up 6 gigahertz for unlicensed use. Of course, this spectrum was not completely free, and it had some incumbents. It had some technologies that were using the spectrum in the past, and there are some technologies in the U-NII and U-NII 7 bands. These are the satellite link communication, geolocation, and other things. So these technologies were using this particular spectrum in these bands. And then we had point-to-point microwave links and wireless backhauls, critical services, utilities, public safety, and so on, that were using these bands and the licensed spectrum. Right? And we also had the U-NII 6 and U-NII 8 bands, which we used for mobile services, mobile trucks, cars, news channels, and so on. They have been using these channels in the past, this spectrum in the past, or currently they're also using this spectrum for various types of communication. Now, of course, what that means is APs are now allowed to operate in this spectrum, but as long as they follow certain rules. Now, this is the same thing that we learned with DFS, when there are certain channels that were opened up in 5 gigahertz band, where we had radar communication. APs were allowed to use that spectrum, but only if they comply to certain rules. In one of the previous sessions, we talked about that. The same concept applies here. So either the APs can transmit at a very low power, in which case they will not be interfering with these technologies, and they're operating only indoor, or they can transmit at standard power, but they follow certain rules if they want to be being used outdoors. So there are various rules that apply to the use of this spectrum, and we'll go through that in more detail to make sure that we're not interfering with any of the incumbents. So if you look at the Wi-Fi 6 gigahertz equipment, which is basically the access points and the stations, they are now divided into multiple classes. Again, the classes were created to comply to the transfer power rules. The first category of access points is the what we refer to as the low power indoor or LPI access points. So these are supposed to be operating only indoors, like residential class access points, for example. They'll be transmitting at a very low energy, 6 gigahertz spectrum, and which means that they will most likely not be interfering with any of the incumbents, any of the external technologies that are currently using the 6 gigahertz. So we transmit at a very low energy. There are no detachable antennas. You should not have any detachable antennas, which means that the reason why they do that is so that you don't connect any external antennas or amplifiers to these access points. So no detachable antennas, no weatherproofing, which means that this is not ruggedized. The idea is that this access point is only used indoors and it's connecting to the wired power. So there are certain restrictions for this class of access points that would be operating under low power indoor. Now, if you meet all these requirements, then you don't need any other, basically following any other rules. You can still operate in the 6 gigahertz spectrum successfully, as long as you're following the rules of power and all the things that are mentioned here. The next category would be basically the standard power access points. These could be used both indoor and outdoor. So I would say most enterprise access points would like to fall into this category because in some cases you want to use standard power indoors. Also, if you have any outdoor access points that are installed outdoors, then of course they will want to use the standard power mode. The standard power will be transmitting at the highest amount of allowed power in the 6 gigahertz spectrum, and the APs are allowed to use that as long as they are controlled by what we call as the AFC database, which we will talk about in a few minutes. And these access points will also be required to have geolocation, so they should have like ability to track the GPS coordinates, and there are other restrictions on these access points. And then we have the very low power access points, which is another equipment class. This can be used for both indoors and outdoors. This is much lower energy even than the low power indoor access point. The use case here is, let us say you have basically in-car Wi-Fi, where you have an access point inside the car that is connected to a 5G network or cellular network, and then it is providing Wi-Fi access within the car. So in some ways it's acting like an access point, but it's very, very low range. It's literally like 1 or 2 feet away. Right? So in that case, you can operate in very low power mode, and that is the other operating class that you have for both indoor and outdoor use, where the range is very, very short, but you're acting as an access point. Right? So that is another category of where you have for access. And then when it comes to stations or client devices, the client devices are basically the mobile clients can connect to both low power indoor access points. They can connect to standard power access points. But when they connect to either one of these access points, they are basically controlled by the rules that apply to those access points. So one of the rules is that the mobile client needs to be transmitted at 4x less power, so 1/4 power of whatever access point it is currently connected. Right? It could be a low power access point or standard power access point, so there's no necessarily like AFC rules and things like that for the devices themselves, but they are governed by the rules by the access point. So the rules apply to the AP, and if the station connects to the access point, then as long as it follows what the access point is telling it to do, then it's fine. So generally, the client is required to transmit at 4 times less power than the AP is connected. And then we also have another class which is called as subordinate indoor devices. Again, the same rules as the standard the low power access point, low power indoor access points apply. These devices are designed to actually connect to other devices in the home that are connected to the network. They themselves don't have internet connection. So these could be devices that are IoT devices, home automation devices, and so on, that are operating on Wi-Fi frequencies, but they're not necessarily directly connecting to the network. They're probably connecting to some form of media gateway or something that connects to the network. So that's another device category. And then we also have the fixed outdoor device category. Again, for this device category, it's most likely used for outdoor mesh networks, outdoor bridging, and so on. And the same rules as standard power access points will apply, and these are attached to a structure, and they can also be acting as stations or devices to connect to other access points. So these are the various equipment classes or categories, both access points and the station side. And if you look at which channels they can operate in, the standard AP, power AP, can transmit at a maximum of 36 dBm with AFC, and we're going to talk about what AFC is in a minute. And they can operate in these bands, U-NII and U-NII 7. Right? They cannot operate in these other bands that are available in the 6 GHz band. And even in this band, they are only able to communicate if they are within the AFC's rules. The low power indoor access points, as we mentioned, are at 30 dBm maximum transmit power, but they don't need any AFC, but they can operate in the entire spectrum, 6 GHz spectrum, as long as they're following the low power rules. And then we have the very low power access points and the client devices themselves, as I mentioned before. So if you can see in this table again, you see that the standard power APs are using U-NII and U-NII 7. They are controlled by AFC, and they can do a maximum of 36 dBm power. And then the low power indoor can do 30 dBm, and it can operate on all the bands. The mobile clients can operate on all the frequency bands as long as they follow the rules that are set by the access points themselves. So that is basically a little bit more detail about how the 6 GHz spectrum can be used by the various equipment classes, device classes. Now let us talk a little bit about automatic frequency coordination, or AFC. So the idea here is that if your access point is operating in standard power, and it could be either indoor or outdoor, there is a chance that it might interfere with one of the incumbent technologies that is used in that spectrum. We talked about the incumbents in one of the previous slides. So how do you avoid that interference? And of course, you want to make sure that the incumbents get the higher priority. So in DFS, what we have done is basically locally you would detect a radar signal, and then you would back off, and that was the method that was used for DFS. But AFC uses a little bit more modern, more intelligent mechanism. So the idea here is every AP that is operating under these rules need to be able to provide their geolocation. So of course, if the APs are indoor, then they can connect to a controller, and the controller can provide the geolocation. So the APs themselves don't have to provide any geolocation. So they don't have to be providing their geolocation. But of course, the controller that is controlling this cluster of APs should be able to provide its location. Similarly, if there are APs that are standalone or they're outdoors, they should have ability to find the GPS coordinates and provide the location. So what happens is, at regular intervals, either the access points or the controllers would basically send a message to someone called as an AFC operator, and it will send a request asking for which channels are available in the 6 GHz for them to use. So the AFC operator could be some third-party entity that is kind of managing the various AFC databases and getting information from the various databases on the internet. So let us say the access point once every 24 hours sends a request and asks for a list of available channels in that physical location, right? So then the AFC operator would query the database, and the database gets data from various fixed link operators. So the incumbent technologies would also provide that information to the database, and they will say if they're operating, what is their schedule of operation, and if they're operating in that frequency and in any particular frequency, and in what location they're operating. So that information is collected over a period of time. So location, time, and which fixed link operator is operating in that location at that time. All the data is collected and is provided to the AFC operator. So the AFC operator then says, okay, so at this point in time today, these frequency channels are being used by the incumbent technologies in this physical location, which means that any AP that is operating in that physical location cannot use those channels, and it can use these other channels. So that AFC operator will get that information and respond back to the access point saying, so these 6 GHz channels, these 3 6 GHz channels are available. for you to use today. Now, tomorrow the database might change. Maybe the fixed operators or the incumbents may not use those frequencies anymore. That will change, could change on a regular basis. But that is the reason why you query the database on once every 24 hours and try to find the channels that are not being used by the incumbents. And based on that, you would use the channel. So that's fundamentally how AFC works. So for this to work, the AP should be able to determine the geolocation. They must request a list of available channels at least once every 24 hours. And APs might share when they request, they will share their geolocation. They will share some information about the error margin of their geolocation. And also they will send their serial number, the FCC ID, and all other details to authenticate with the AFC operator, because you don't want some rogue APs to connect to an AFC operator. So of course there is some form of a security process there, right? And the AFC operator, as I mentioned, will manage the dynamic database of all active RF activity from the fixed link operators, and they will make the channel availability decision based on the dynamically changing data, right? And that is the idea of AFC. We're really leveraging the cloud and the fact that we have super fast internet these days, and using the cloud technology to really make this thing happen. So that's the basics of AFC. So now all standard power access points should be following the AFC rules. Okay, so now we know that 6 GHz spectrum, and there are 1200 megahertz of spectrum available. 6 GHz, we can use it for many things. So what are the most promising use cases? We have to remember that most of the existing deployments are still in 2.4 and 5 GHz, and most of the devices that are there are still in 2.4 and 5 GHz. They will be even though we have many APs that are operating in 6 GHz now, not many stations are operating on 6 GHz, right? So then what are the most promising practical use cases, at least in the short term, for 6 GHz? One of the most promising use cases is what we refer to as mesh backhaul, right? This is where, let's say, you have an access point that is providing Wi-Fi access to multiple clients in your area, and the access radio could be 2.4 or 5 GHz radio, because the client is also 2.4 or 5 GHz client, and so the client is connecting to the access point. It can connect and transmit in 2.4 or 5 GHz. But if this is already a 6 GHz access point, since we're installing 6 GHz access point, the access points can talk to each other using 6 GHz, especially when they're in a mesh network. So if you have deployed 6 GHz, the access points that support 6 GHz, even though the stations are not 6 GHz capable, the access points can talk to themselves over the mesh backhaul using 6 GHz. And so 6 GHz mesh backhaul is a very promising use case, because there is so much available spectrum, which is basically greenfield spectrum. And if there are two entities, two access points able to talk 6 GHz, then they can very easily talk to each other with very less interference, right? Because they're not interfering with anything in 2.4 or 5. So 6 GHz mesh backhaul is a very interesting use case. And then there are other market verticals, such as let's take a hospital, or maybe someone is setting up a new warehouse or a new factory or something like that, where there are a lot of application-specific devices that can purely be on 6 GHz, right? So, for example, if we take the example of a hospital, they could have all modern devices, and they could maybe all be operating on 6 GHz. And the hospital might say that all these devices, the communication is very mission critical. So I'm going to put all my devices and all my access points in 6 GHz band, and the guest networks, people coming to the hospital, the guests and things like that, can stay on 2.15. But all the critical care apparatus, patient monitors, infusion pumps, and all these other defibrillators and all this equipment can be upgraded to 6 GHz, and you can create like a basically a greenfield 6 GHz network to have uninterrupted access, right? So there are any new setup that you're making, any new use case, that's where 6 GHz can be used quite a bit. Of course, we have very high bandwidth applications like AR, VR applications, things like that require a lot of bandwidth, and this is where the modern devices can come with 6 GHz radios, and when they come with 6 GHz radios, then they can leverage the full potential of 6 GHz spectrum. And another example would be like where we have again industrial robots and things like that, so where you're using this model where, let's say you have a robot that is connected to various elements on the robot device itself, and it is basically connecting to the network using like a bridge mode, right? So there is an access point on the robot, and it is providing internet connection to all the elements on the robot. But then it is wirelessly connecting to the network, because it's a robotic device that's mobile. It cannot have any wires fixed to it. So of course it has to backhaul over Wi-Fi, and it can provide internet connectivity to everything on the robot. So when it is backhauling over Wi-Fi, even though the devices that are on the robot could be legacy devices, the access point itself could be a 6 GHz AP talking to the network that's also supporting 6 GHz. Again, it is a slightly different variation of the mesh backhaul use case. So if you're doing special networks like that for special use cases, then 6 GHz becomes a very viable option. These are some of the use cases which initially 6 GHz can be used. Of course, as we go along, most mobile devices and laptops and smartphones, everything will come with 6 GHz radios, which means that all the standard use cases that we are not already normally using will also be 6 GHz use cases. But initially, as the technology is being adopted, maybe we'll find like very niche specific use cases for adoption. Okay, so another big thing, of course, with the 6 GHz spectrum is the backward compatibility problem is solved in many ways, right? If you looked at if you watched my last presentation, I was talking about the backward compatibility problem with Wi-Fi. As we keep increasing the speeds, we went from Wi-Fi 4 to Wi-Fi 5 to Wi-Fi 6 and so on. But since the devices themselves have to be backward compatible, we always had basically backward compatibility issue. But that problem doesn't exist in 6 GHz, right? The idea is that if you have a 6 GHz access point that's operating in 6 GHz, then only 6 GHz devices can connect to them. So if you don't have, so that is the only possibility. So then you cannot have a 6 GHz legacy devices on 6 GHz band, because all the devices should be 6 GHz capable, which means that they will be supporting the latest technology, which is Wi-Fi 6, which means that they will be supporting 1024 QAM, which means that they will be supporting OFDMA, multi-MMO. So all the features that you got in Wi-Fi 6 will come automatically with all the devices that operate in the 6 GHz band. So there's no necessarily backward compatibility problem. So for the first time, you can have a speedway, a really fast racetrack, and all the vehicles that are traveling on it are also race cars, right? That can travel really fast. So the legacy devices problem, at least in some extent, is to some extent solved when you're operating the 6 GHz band. Okay, because of this, we have some new features within the Wi-Fi protocol that are possible because of this, because of the wider spectrum becoming available. Some of these features we'll talk about in the next few slides. One of them is, of course, you can have a native greenfield Wi-Fi 6 mode, because as I mentioned, all the devices that would connect to the 6 GHz band to the 6 GHz access point will have to support 6 GHz, which means that they will actually support Wi-Fi 6 also, which means that they will understand OFDMA, they'll understand HE information elements and so on. So now what you can do is you can have like basically you can remove some of the backward compatibility fields within the PHY header. You can remove some of the legacy fields in the PHY header, and you can only have the HE and PHY and MAC headers, and that reduces the amount of overhead when it comes to the headers themselves. And you can also do much shorter beacons, because remember that the beacons carry a lot of information elements about the current standard and also all the previous standards, right? So now you can remove all the legacy standard information elements from the beacons, and now the beacons can be shorter. So that's one of the things, right? And now we have a different scanning mechanism. So one of the things we need to understand here is just as an example, Wi-Fi 6 GHz has 59 20 MHz channels. So if you are scanning on each 20 MHz channel, and let's say you're spending like 100, 200 milliseconds on each channel, you have to go through 59 such channels. So your off-channel scan time is going to be increased substantially, right? And so with so many channels being available in the 6 GHz band, the fundamental concept of scanning changes. So we all learned about active scanning, passive scanning. Active scanning is where we send probe requests and we wait for a probe response. Passive scanning is where we tune to a specific channel and we listen to beacons. All of that changes fundamentally with Wi-Fi with 6 GHz because the number of channels available is much more now, and so the traditional passive active scanning mechanisms will be very costly because of a lot of spectrum becoming available. So there are some new methods that are designed to reduce this problem. We'll talk about that. And then there are also some security enhancements as a part of 6E. Of course, there are things like PMF, WPA3, and all of that becoming mandatory. Is part of the new things that we have here. Okay, so a few changes with 6 that came with 6 GHz. As I mentioned, shortened beacons because the beacons on 6 GHz beacons can operate in pretty much in HE mode or greenfield mode. So if you look at a normal Wi-Fi 6 HE beacon, like Wi-Fi 6 HE beacon frame, it has all the legacy information elements because of the need for backward compatibility. You will have the HT fields, VHT fields, and all of these things. All of them, again, the idea there is even though the AP is in operating in 11AX mode, it should be able to serve 11AC and 11N clients and so on. So all these information elements are inside the beacons. Most of them can be removed. If in the case of Wi-Fi 6E, and the beacons can be much shorter. And need to remember that a beacon frame is transmitted at very low data rates if it has to be backward compatible, and it can take a lot of airtime. And if the beacon becomes really long, it takes a lot of airtime, right? So now, not only can you reduce the size of the beacon, you should be able to transmit at higher data rates also, because in many ways the spectrum is the AP is operating in a special category and a special greenfield mode. So that reduces the overhead that is coming from beacon. Now, when it comes to scanning, again, the fundamental idea of active scanning and passive scanning changes a little bit with the 6 GHz spectrum. There are two types of scanning we can do. One is what we refer to as the out-of-band scanning, which means that you are scanning for the 6 GHz access points, but that scanning is not done in the 6 GHz band. It is done in the legacy 2.4 and 5 GHz band. So most APs that are deployed, 6 GHz APs that are deployed, also will have 2.4 and 5 GHz radios. So they'll have a 2.4 GHz radio, they'll have 5 GHz radio, they'll have a 6 GHz radio. So let's say a client is connecting and it connected to the 5 GHz radio on this access point, or it is scanning on the 5 GHz radio on this access point. And when it gets the responses from this AP in the 5 GHz band, the AP by that time already knows what 6 GHz channels it's operating on and what SSIDs it has in the 6 GHz. So along with sending the 5 GHz network information, AP and channel information, this AP can also send the 6 GHz information on the same probe response to the client. So this is what is called as out-of-band discovery, where the client is connected in 2.4 or 5 GHz band, but it is getting information about all the 6 GHz APs and SSIDs and channels on the same response. Right. So this is something called as what we call as a reduced neighbor report RNR frame that basically contains information about the 6 GHz networks, and that is transmitting over a 5 GHz probe response. Right? And so this allows the station to never actually go and scan on 6 GHz band. It can always stay on 5 GHz band, connect to the current AP, get a list of 6 GHz APs that are available. And if at some point it wishes to move to 6 GHz, then it already has a list of APs. And so it can select an AP and then automatically associate. And that way you don't spend any time doing off-channel scanning. And that is one method of out-of-band discovery. Now, there is also this new feature called as multi-BSSID. Again, since we have 2.4 GHz, 5 GHz, 6 GHz, we have tri-band radios. And in each band, you have multiple SSIDs and BSSIDs. So sending out one beacon for every SSID BSSID combination will take up a lot of airtime. And so there is this new mechanism called MBSSID or multiple BSSID, where within the same beacon frame, you can advertise multiple SSIDs and BSSIDs. Basically, the shared parameters across all the BSSIDs can come in shared information elements, and the unique parameters for each SSID or BSSID can come in special information elements that are a part of this multi-PCS IEs. So again, we'll show that at the end of the session. We'll show that show an example in packet captures, and then you'll understand this better. Now, when it comes to in-band scanning, which means that you are scanning for 6 GHz APs in the 6 GHz band. Now, this is not needed if the AP has 5 GHz radio. Ideally, you should be able to scan for 6 GHz out of band in using the 5 GHz channels. But let us say this AP is only operating at 6 GHz, or let's say this AP is only a 6 GHz AP, or maybe it's a mesh backhaul AP or something like that, where it's only 6 GHz. In that case, you don't have any choice. The clients have to scan on the 6 GHz, right? So this is called as in-band scanning. So now when you're doing in-band scanning, there are two methods, of course, the standard methods, active scanning and passive scanning. So active scanning, of course, you don't want to go through all 59 20 MHz channels and scan on all of them, right? That takes a long time. So there is a concept called PSC, or basically what we refer to as preferred scanning channels, which means that there are some channels that are picked those are the only channels you need to scan on, and you don't have to scan on all channels. And it is designed in such a way that the APs are basically you'll be able to gather information about the AP by scanning on these preferred channels. Most of the APs, of course, will be in 20 MHz, 40 MHz, 80 MHz mode. So by using these preferred channels, you should be able to get information about those APs instead of scanning on each one of these 20 MHz channels, right? So active scanning is only allowed on select set of preferred scanning channels, and this reduces your active scanning. Passive scanning, there is a new technology method called FILS, or what we refer to as fast initial link setup. And this is where very short frames, action frames, are being sent every 20 milliseconds, basically without even being asked for them. The AP can send these frames, and then the station, when they tune to these frequencies, they can actually listen to these short action frames, and these action frames will have very quick information about the 6 GHz access points. And by shortening that and transmitting that at more regular intervals, you can shorten the passive scanning time on each channel, and that technology is called FILS, or fast initial link setup. So this is also another concept that is part of the in-band scanning mechanism that we have in 6 GHz. To summarize, we talked about the 6 GHz spectrum that is opened up. Now we have 400 MHz of spectrum, which is awesome. It creates so many opportunities for Wi-Fi. But of course, there are incumbent technologies in this space, so we need to follow certain rules. And so the device categories have been created, different classes, indoor, out, low power, standard power, and so on. So if you're doing standard power operation, you need to follow AFC rules. We talked about what those AFC rules are, and then there have been some new features that have been added to because of the new channels that have opened up. We talked about preferred channel scanning. We talked about FILS. We talked about out of band scanning using R&R, and all these things are the new things that have been added for Wi-Fi 6E. There are a lot of really good material available. Most of the material I gathered are from some of these links. Some really good videos available, and some really good white papers available. And they go into a lot more detail than what I went through and explain. They did a very good job. So I would definitely recommend, if you're interested in this topic, to go back and pick up some of these links and watch these videos and read these papers. So that is all I had for this session. What we will now do is I'll hand it over to one of our team members here, Bhavya, so that she can go through some of the example packet captures that demonstrate some of these features. And then after that, we'll jump into Q&A.
Thank you so much, sir. 1 second, I'll be sharing my screen. Hope my screen is visible. Hello, everyone. Thank you so much, sir, for giving an overview on many exciting features on 60 gigahertz. So now let's consider one scenario where there is an AP, which is a tri-band AP. It is having 2 gigahertz band, 5 gigahertz band, and 6 gigahertz band as well. So as Sir mentioned just now, we have different scanning mechanisms. Firstly, talking about out of band scanning mechanism. So here I have a few packet captures about the probe response from 2G band. So and also I have some beacon frames from the 2G band. So let's get into one of the probe response from 2G band. As you can see here, the frequency is 2412. That is it is being transmitting in the 2.4 gigahertz band. So while I'm receiving a probe response from the EP in the 2.4 gigahertz band, I also have a tag called reduce neighbor report. This tag can be found in probe responses and as well as in the beacon frames as well. So what does this tag actually contain information about? So generally it contains the information about the 6 gigahertz band that is available in the EP. So without actually without actually going into the 6 gigahertz band, using the 2.4 gigahertz and also using the 5 gigahertz band, we can get the information about the 6 gigahertz. So let's get into the packet level. What are the information present? So here we have some TBTT information fields. These are nothing but the SSID information elements of the 6 gigahertz. So in this AP, I have configured I have configured 8 6 gigahertz band SSIDs. So that's why I'm seeing here 8 fields of TBTT information. So what is this channel number and operating class? So this channel number indicates at what channel the SSIDs that are configured in the 6 gigahertz band are operating. So I can say that the SSIDs are in the channel 65. That is, they're operating in the 6 to 75 megahertz band, and they're so how to know on what bandwidth they're operating? That will be helped by operating class. So these are the operating class values are prefixed, like they're standardized. Like for example, if I have 131 as my operating class value, then my IP is operating in 20 megahertz. So in the packet capture, I have my operating class in 134. That is, my AP is operating in 160 megahertz bandwidth with a center frequency with a primary channel as 65. So let's get into the SSID level information. So here I have 8 SSIDs configured. So let's check about first SSID. So here I have some fields like BSSID. This BSSID is the MAC address of the interface and short SSID. Here in the reduced neighbor report, we won't be having the exact SSID name. We will be having the short SSID. So what is this short SSID? This is nothing but the CRC32 checksum of the actual SSID. Here in reduced neighbor report, we won't be transmitting the actual SSID. Instead, we will be transmitting its CRC32 checksum, which will be named as short SSID. We can also see some BSS parameters. We in few access points, we have an option where we can set the same SSID name for 2 gigahertz band, 5 gigahertz band, and 6 gigahertz band. And in few APs, it's different. So here, this same SSID field will let us know if the SSID is same for all the bands or not. Here I configure different SSID names for different bands. So this bit is set to false. In case if I configured the same SSID for all the bands, then this bit indicates that true, indicating that we have same SSID for all the bands. And also, Sir shared some interesting concept like multiple BSSID. So here in this API, I've configured the multiple BSSID feature as enabled. So I'm seeing this. So I can know about the information of the multiple BSSID field feature is enabled or not through using this bit. And also the 6 gigahertz, like in the 2.4 gigahertz, we are getting this information. So this 6G information might be of the same AP, or it might be the information of the 6G SSID from different AP as well. So how to know that can be known using the co-located AP. So here the co-located AP is a bit is turned to true. That is, this SSID information which it is giving is in the same AP in which the 2.4 gigahertz SSID is there. So similarly, for other SSIDs also, I have the same information. So for and BSSID, short SSID, as they are different, the information will be varying. So this is about reduced neighbor report. This is the outband scanning mechanism. So let's get into some inband scanning mechanism as well. So as Sir mentioned, we have FILS, which is one of the passive scanning mechanism of 6 gigahertz. So here you can see that I'm actually the FILS is being sent in the 6 GHz band itself in the frequency of 6295 megahertz. So this is an in-band scanning mechanism and it is a passive scanning mechanism. So what are the fields in here? We can see that we will be having a frame control field. This frame control field is nothing but it will say what information is present in this FILS packet. So here I can see that there is an SSID length, means the SSID length is present in the this FILS packet, and we have also capabilities, and even in, same as like we saw in the reduced neighbor report, the actual SSID won't be sent in the FILS frames as well. Here also we will be seeing the short SSID being transmitted. This again repeating it, the short SSID is nothing but the CRC32 checksum of the actual SSID. And also we can see the RSN information and other information what is present in this particular particular FILS packet we can be seeing over in this frame control field. And we can see the beacon interval. What is the beacon interval set to the AP? As we can see, it is the default beacon interval, that is 102.4 milliseconds. So we can see the short SSID is being transmitted instead of SSID as mentioned. And there are some like other information like at what bandwidth it's operating. So here 3 bits are used to tell at what bandwidth it's operating. Here we can see the 3 bits are set to 011. That is the value is 3. The value 3 indicates 160 megahertz. Similarly, if the 3 bits indicate 000, then it is saying that the AP is operating in 20 megahertz. If it is 1, it is operating on 40 megahertz. If it is 2, it is operating on 80 megahertz. Similarly, it is 3, so it is currently my AP is on 160 megahertz bandwidth. And we can also know how many spatial streams the AP is actually supporting using another 3 bits. Here, my AP is supporting 4x4 spatial streams. So the value is set to 3. If it is set to 0, then it is operating on 1 spatial stream. If it is 2, if it is 1, it is operating on 2 spatial streams, so on. Here we can also see phi index value. So here phi index value, it determines what mode it is operating on. Like if it is operating on HT, if it is operating on VHT, if it is operating on HE mode, that will be specified by the phi index field. We also contain the RSN information in the FILS element over here. And we have some transmitted power elements in the tag parameters as well in the FILS field. So now let's get into some interesting feature that is present that Sir suggested. So I configured 8 SSIDs in 2G frame. What am I seeing? I'm seeing multiple beacon frames for each SSID. So this is making the channel, even though I'm not running any traffic, there will be some amount of channel utilization because of this beacon frames. So for multiple SSIDs, instead of sending each beacon from each SSID, what if we have a single beacon for all the SSIDs? So that is nothing but multiple BSSID feature that Sir mentioned initially. So here I configured multiple BSSID feature, and here I can see that multiple SSID information is sent in the single beacon frame. So let's get into this. Here we can see that there is one SSID which is we can call it as transmitted SSID. So this is the main SSID that will be sent this. And the other now in this API I have configured 8 SSIDs. The other SSIDs information I'm sending using the same beacon frame. How it is being sent, that is in the multiple BSSID frame. So all other parameters like supported rates and some HE capabilities, these all will be unique. These all will be same for all the 8 SSIDs. So these will be not sent multiple times. These will be sent only once, but there will be some unique things like the SSID name might be unique and the RSN information might be unique. So those frames will be transmitted. So how are they getting transmitted? You can see them under these tags called multiple BSSID. So let's get into them. Here we are seeing multiple sub-element non-transmitted BSSID profiles. That is, as I already mentioned, the main SSID we are considering as transmitted BSSID. All the other SSIDs we call them as non-transmitted SSIDs. So here in this sub-element we have the information that are unique that to the main SSID. That is to the main transmission SSID. What are unique parameters that will be transmitted inside these sub-elements? So let's get into it. We have the SSID name. The SSID name is unique from the transmitted BSSID. So this will be sent. And not only this, the RSN information, that means the SSID1 might be operating on SAE, whereas the SSID2 might be operating on enhanced open, that is OWE encryption. So in that case, the RSN information might be different. So RSN information will be sent. And also multiple BSSID index. Using this multiple BSSID index, we can calculate the BSSID of the particular SSID. So this is the tag where we are using for knowing the BSSID of the non-transmitted SSIDs. So similarly, we will have all the information for the other configured SSIDs as well. I hope you guys enjoyed this packet capture analysis. Over to you, sir, for queries.
Thank you, Bhavya, for the detailed explanation. I think that's all we have for this session. Hope you found this useful.